Hello and welcome to this Success Factors webinar titled Design of Plant Foundations Using STAAD Foundation Advanced. My name is Sye Chakraborty and I am part of the technical support team at Bentley Systems. In this webinar, we are going to look at different types of foundations that you can design in STAAD Foundation Advanced using the plant mode. Before I begin, I would like to mention that you need to have a STAAD Foundation Advanced license to be able to access the plant mode in STAAD Foundation Advanced. The supported plant foundation modules include foundation for vertical vessel, foundation for horizontal vessel, foundation for vibrating machinery, ring wall foundations for storage tanks, laterally loaded drill pier. We're going to look at all of these foundation types in this webinar. So let's get started. The first plant foundation type we're going to look at is the vertical vessel foundation. Here is a list of codes that STAAD Foundation Advanced refers to when it comes to design of these foundations. PIP STE 03350 is the main reference used. Wind and seismic loads can be directly input by users, or you can ask these to be calculated as per the ASC 7 when designing as per the US code. Similarly, for users designing as per the Indian code, you can have the wind load generated as per the IS 875 Part 3 and seismic as per IS 1893 Part 1. Concrete design is based on ACI 318 or IS 456, depending on which country you are using. Load combinations can be generated as per the PIP STC 01015 or ASCE. Here are the foundation and support types that are available. You can design both octagonal and square foundations. Also, the foundations could be supported on soil or on pile caps. Let us look at the different aspects of the design now. First comes the design of pedestal. STAAD Foundation Advanced can design octagonal pedestals. It checks the pedestal size as per the requirements outlined in section 4.5.1.1 of STE 03350, which provides a bunch of equations involving the bolt circle, bolt diameter, the sleeve diameter, etc., as you can see in the slide. Continuing with the pedestal design, here are the main checks performed. Based on the overturning moment and the axial force at the base of the pedestal, the software calculates the tension in a single dowel bar and chooses a dowel bar size so that it can take up this tension. The software also ensures that a minimum reinforcement requirement is satisfied for these dowels. And the same is also satisfied for the ties as per clause 4.5.5. Reinforcing steel is also provided at the top of the pedestal as per section 4.5.6, and a minimum of number 4 bars at 12 inch on center are provided in each direction. SFA calculates the projected concrete failure area for an anchor bolt or group of anchors within the pedestal as per the figure A of STE 03350. A circle equivalent in area to the octagonal pedestal is used for this calculation. This slide shows one of the many configurations that are provided in the code document. The configuration that provides the largest AN is the one that is considered. The pedestal may need to be resized based on this requirement. The software also calculates the compressive force developed over this area and ensures that that is less than the allowable compressive strength of concrete. Serviceability checks include checks for sliding and overturning and soil bearing checks. Sliding and overturning are checked as per the section 4.7.4 of the STE 03350 document. Sliding ratio, or in other words, factor of safety against sliding, is obtained by calculating the ratio of the restoring force to the disturbing force. For overturning, the stability ratio is calculated as per the equation 15. The minimum factor of safety for both sliding and overturning should be 1.5 as per section 4.7.4 of STE 03350, and STAAD Foundation Advanced does check that. Soil bearing checks are carried out as per section 4.7.2 for octagonal footings and 4.7.3 for square footings. For soil bearing checks, we check the actual bearing pressure on the diagonal and compare that to the allowable bearing capacity. The eccentricity is calculated as the ratio of the overturning moment at the base of the footing divided by the axial load, and the E by D ratio is determined. Here, D represents the distance between the parallel sides of the footing. When E by D is less than 0.122, the entire area of the footing is in compression, and we use the first set of equations for calculating the pressure F. The second equation in the first set is only a modified version of the first equation. For E by D greater than 0.122, only part of the octagonal footing is in compression. We refer to the figure B as seen here on the right to find out the L and the K, and then use the equation 11 to calculate the F value. Strength checks are carried out as per the guidelines of the ACI 318 and also the PIP STE 03350. For strength design, soil bearing pressure needs to be calculated on the flat as opposed to being calculated on the diagonal, which was the case for the bearing pressure check. Otherwise, it's pretty much the same set of equations, just the E by D limits are a little different for this check. For E by D values which exceed those provided in the figure B, one can find out the K and the L values from the table 2 as seen here to evaluate F using the same equation 11. Strength checks are carried out as per the guidelines of ACI 318 and also the PIP STE 03350. If the pedestal is octagonal, an equivalent square pedestal having equal area is calculated. Moment is checked at the face of the equivalent square pedestal. One-way shear is checked at a distance of D from the face of the equivalent square. Both moments and shears are calculated considering a 1 feet wide strip and as if it is supported as a cantilever from the edge of the equivalent square pedestal. Punching shear is checked at a distance D by 2 from the face of the equivalent square pedestal. The software checks that the footing is thick enough to allow for enough embedment of the pedestal dowels. It also checks that the footing is wide enough to accommodate the development length of bars from the face of the pedestal. I included this slide just to show a typical reinforcement detail of an octagonal footing for a vertical vessel supported on soil. Let us now get into the software STAAD Foundation Advanced and see how we can define the vertical vessel foundation using a very simple wizard-based input. In the first page, as seen here, you can provide a name for the job or vessel ID, choose the unit system, and also choose the design code. And then if you are designing as per the US code, you can choose the version of the code. In this page, you get to define the shape of the foundation, octagonal or square, and whether it's soil supported or supported on piles. You also get to define the vessel geometry, pedestal geometry, and geometry of the footing. If you want STAAD Foundation Advanced to come up with the footing dimension, you can provide a minimum and maximum value of the diameter and thickness and provide an incremental value for these items. You can also account for soil above the footing and any buoyancy effect caused due to the water table. This page allows you to define the details of the anchor bolts, which are then used to determine the pedestal dimensions as per the guidelines provided in section 4.5 of the PIP document. This is where you input the loads, namely the empty load, the operating load, test loads, including any loads that the foundation may be subjected to during the erection. You can even add additional loads if required through the table below. All of these loads are considered to act at the top of the pedestal, and so any additional moments that may be caused due to the horizontal shears or the base shear as it is called here would be considered by the software automatically for the design of pedestal and the footing. Another thing to note here is that you need to use negative sign for the loads to ensure that these are considered to act downwards. In the next page, you would enter the data related to the wind load generation. You have the choice to specify the shear and the moments due to the wind directly. Else, if you choose the program calculated wind load, you can input the basic wind load generation parameters and the software would generate the wind load based on the ASC 7 or the IS 875 Part 3. The partial wind case percentage is used to tell the software how much of the wind load it needs to consider for the test condition. This page lets you define the time periods which are subsequently used for the wind and seismic load calculations in case you asked the program to calculate those loads for you. You have a few options for entering the time period. You can choose direct input option to directly enter these periods yourself. Else, you can get the software to calculate the period using an empirical formula, and for that, you need to provide the mass input through these tables. The next page is for seismic load input, where you can directly input shears and moments due to seismic load yourself, both for the operating and empty conditions. Else, you may let the software calculate the seismic load, and for that, you may choose either the mass table CG or the user-defined CG. In case of the mass table CG option, the mass data entered in the previous page for the time period calculation will be used by the software to calculate the CG of the vessel. In case of the user-defined CG option, you can directly input the CG. For calculating the seismic loading, you can choose the zip code or specify the spectral acceleration parameters yourself based on which the software can calculate the seismic loads. In this page, you're going to define the load combinations. Automatic load combination generation as per ASC 7 and PIP standards are available for you to choose from. You can check out the combination factors from these tables, and in case needed, you can also define your own combinations using the user-defined option. In this final dialog box, you're going to input the densities for concrete and soil. Density of water is only required to be input in case you are considering the buoyancy effects. You are also going to enter the minimum stability ratios, allowable bearing pressure, and coefficient of friction, all of which are associated with the stability or serviceability checks. The final set of parameters at the bottom of the dialog box are related to concrete design. Once you are done filling out all of this data, you can just go and run the design. The software then runs through the design process and generates the calculation sheet. As you can see, the calculation sheet provides the details of the calculations. So you have the input parameters listed first, followed by all the loads, then the wind load and seismic load, followed by the load combinations, and then the pedestal design, eventually followed by the footing design. You can also go to the detailed drawing by choosing the detailed drawing option. The detailed drawing generated this way can be passed on to the detailers for further detailing work. That completes the design of the foundation for vertical vessel. We now move to the next planned foundation type, which is foundation for the horizontal vessel or heat exchangers. Here is a list of code references that STAAD Foundation Advanced refers to when it comes to designing this type of foundations. This slide lists the major loads considered for the design. These loads can be broadly categorized as vertical and horizontal loads. Details on these loads are available in section 4.2 of PIP STE 03360 document. In the next few slides, we are going to discuss how the loads are distributed between the channel end or the sliding end and the shell end or the fixed end. As per section 4.2.1.3 of PIP STE 03360 document, for most common heat exchangers, 60% of the vertical load is considered to act at the channel end and 40% is considered to act at the shell end. The wind load is generally considered to be equally distributed between the supports. This slide explains how the seismic load is distributed between the piers. The friction resistance at the sliding end dictates the distribution as outlined in this section 4.3.2.3. For slide plates with lower friction or coefficient of friction lesser than 0.2, the entire load is applied at the fixed end. For slide plates with higher friction or coefficient of friction greater than 0.2, 70% of the seismic load is applied at the fixed end and the remaining 30% is applied at the sliding end. This slide explains the thermal load distribution between the piers. As per section 4.3.4.2 of the PIP document, when the static friction developed at the sliding end under normal operating condition is less than the force required to deflect the pier by half of the thermal growth between the supports, thermal force is assumed to be equal to the friction force, and the same force is considered at both piers. Now coming to the distribution of bundle pull load, section 4.3.3 of PIP refers to section 4.1.8 of the PIP STC 01015 document, which specifies that the portion of the bundle pull load at the sliding end support shall be equal to the friction force or half of the bundle pull load, whichever is less. In this slide, the friction force at the sliding end is assumed to be equal to the thermal force. So if half of the bundle pull exceeds the thermal force at the sliding end, the bundle pull load considered at the sliding end is equal to the thermal load. The remaining portion, which is bundle pull force minus the thermal load at the sliding end, is considered to be the bundle pull force at the fixed end. On the other hand, if half of the bundle pull load is lesser than the thermal force at the sliding end, the load due to bundle pull is equally distributed between the sliding and the fixed ends. Here are the list of design checks carried out, which are as per the guidelines provided by the PIP 3360 and the ACI 318 codes. This slide shows a typical reinforcement detail for a horizontal vessel foundation. Let's now see how we can define the horizontal vessel foundation in STAAD Foundation Advanced. Just as for vertical vessel foundation, for horizontal vessel foundations also, the software has a similar wizard-based input. You can provide a name for the job or vessel ID, choose a unit system, and choose the design code. You can either have a single exchanger or have one exchanger stacked on top of another. In terms of footings, you can have a combined footing for both piers, which is typically used for short exchangers or vessels, or you can have individual footings underneath each pier. For isolated footings, you can even define a strap beam connecting the footings. The footings can again be soil supported or pile supported. In addition, you can specify all the geometry information related to the exchangers, like the length and the diameter of the exchangers, spacing between the exchangers, in case you have these stacked, height of the piers, depth of the soil above the footing, etc. In this page, you would specify the footing geometry information like distance between the piers and length and width of each pier. You can have the software iterate and come up with a foundation size for you, in which case you would specify the minimum and the maximum values for length, width, and thickness, and specify the dimension increments it may consider for each iteration. You can also specify a definite footing size and have the software check the adequacy of that, in which case you would specify the same values for minimum and maximum dimensions and also declare the overhangs and the footing width as fixed. This is where you specify the loads corresponding to empty, operating, or test conditions. The pier load distribution percentage lets you tell the software as to how the loads are distributed amongst the piers at the shell end and the channel end. As we discussed earlier, the default distribution is 60% at the channel end and 40% at the shell end. You can specify the erection loads, if any. Also, thermal loads and bundle pull loads may be specified here. The software would account for the moments due to lateral loads automatically. You would also be able to define any additional user-defined moment if required. In addition, you can define the slide plate friction coefficient, which determines how the different lateral loads are distributed among the piers. We have already discussed that before in this webinar. In the next dialog box, you would enter the data related to the wind load generation. This dialog box is exactly similar to what we had seen for the vertical vessel foundation, so I'm going to jump to the next page. This page is for the seismic load input, which again is exactly similar to the page we had for vertical vessel, so I'm going to skip this one. Just as for vertical vessel, here also you can define automatic load combinations as per the ASC 7 and the PIP standards. In case needed, you can also define your own combination using the user-defined option. In this final dialog box, you're going to input the densities for concrete and soil. You're also going to enter the factor of safety against sliding and overturning, coefficient of friction, and bearing capacity, all of which are associated with serviceability and stability checks. Also, you're going to set the design parameters related to concrete design. Once all inputs are completed, then we can simply run the design And once the design is finished, we can go to the calculation sheet to check the details. As you can see, the calculation sheet provides the details of all the calculations that the software has done for this foundation. Finally, you can go to the detail and schedule drawing and choose the detail drawing option, where the software would give you a detailed drawing that can be used for further drawing generation process. That completes the design of foundation for horizontal vessel. Next, we move on to vibrating machine foundations. STAAD Foundation Advanced can be used to design foundations for vibrating machinery as per ACI 351.3R-04 guidelines. The basic goal of designing a machine foundation is to keep the vibration amplitudes within certain limits to ensure that the machine can perform satisfactorily and excessive transmission of these vibration effects to the supporting structures and soil is prevented. Vibration caused by the operation should not cause any discomfort to people operating in the vicinity of the machine or to equipment that may be around. Another very important objective is to size the foundation and design it such that resonance effects can be prevented. We will talk more about the resonance later in this presentation. The software can analyze different types of foundations like single block, combined block, and combined block with gearbox. Both rotating and reciprocating machine types are supported. The reciprocating machines can only be supported on single block foundations. The machine foundation is subjected to both static and dynamic loads. In static load, you would enter the machine weight as obtained from the manufacturer. The software would calculate the weight of the concrete foundation. As far as the dynamic loads are concerned, the unbalanced force can be directly obtained from the manufacturer. Else, for rotating machines, if you get the machine eccentricity from the manufacturer, you can input that and have the software calculate the unbalanced forces based on ACI 351 clause 3.2.2 equations 3-3 and 3-4, which are shown in this slide. Else, if no force or unbalanced information is provided by the manufacturer, you can have the software calculate the unbalanced force based on the rotating weight and the operating speed of the machine as per the clause 3.2.2 equation 3-7 shown here. This slide shows the equations that are used by the software to calculate the unbalanced forces for reciprocating machines. The first equation, 3-18, represents the unbalanced force parallel to the direction of movement of the piston. The first part of the equation, that varies with the frequency of the rotation omega 0, represents the primary force, and the second part, that varies at twice the frequency of rotation, represents the secondary force. The equation 3-19 represents the unbalanced forces perpendicular to the piston movement. As mentioned before, these are only used if you ask the software to calculate the unbalanced force as opposed to directly entering those. Dynamic analysis of machine foundation requires computation of soil spring stiffness and damping. Before we move on to see how these are actually calculated, let's take a quick look at some of the terms which are used in these calculations. For the analysis, a square or a rectangular foundation is often considered as a circular foundation with equivalent properties. For the three translational directions, the equivalent circular foundation is determined based on an equivalent area, and radius is calculated as shown in equation 4-9a. Another term that is used in these calculations is a dimensionless frequency as shown in equation 4-11. Now coming to the actual calculation of the soil springs. In STAAD Foundation Advanced, you can input these using any of the three methods as mentioned in this slide. If the soil spring stiffness and damping values are provided by the geotechnical engineer, you can directly input those. Else, you can choose the Richard Whitman method or the Vellet-Sauce method as outlined in the ACI 351 and let the software calculate these values for you. The relevant section numbers where these methods are discussed in the code has been provided here. Here we can see the equations used for calculating the damping and stiffness as per Richard Whitman method. As noted here, this method is best suited for scenarios when the dimensionless frequency is between 0 and 1. It is worth mentioning here that these dynamic analysis problems are addressed either with real domain mathematics or with complex domain mathematics. Richard Whitman method represents a real domain solution in which the stiffness and damping are represented as constants independent of the frequency. The equations 4-12a and 4-12b are used to calculate the mass and damping ratios for vertical and horizontal translation directions. STAAD Foundation Advanced does not consider rocking or torsion degrees of freedom, and so equations for those are not being discussed here. The 4-13a and 4-13b are used for calculating the stiffness, and subsequently based on the damping ratio, system mass, and the stiffness, the damping constant is calculated as per equation 4-14. This slide describes the Vellet-Sauce method, which is based on complex domain mathematics. This method, unlike Richard Whitman method, is dependent on frequency and applicable for dimensionless frequencies up to a value of 2. If you look at the generic form of this equation, there is a real part and an imaginary part. The real part represents the soil stiffness and the imaginary part represents the damping. Equations 4-15a represent the horizontal stiffness. Equation 4-15c represents the vertical stiffness, and the terms like alpha 1, gamma 2, which are dependent on Poisson ratio, are taken from the table 4.1. Damping has two components, namely geometric or viscous damping and material or hysteretic damping. The elastic solution methods like Richard Whitman or Vellet-Sauce methods that we discussed before account for geometric damping only, but not the hysteretic damping. One can, however, account for the material damping effects, in which case an adjusted stiffness is computed as shown in equation 4-22. Considering the stiffness to be the real part and damping to be the imaginary part of the equation 4-22, one can easily arrive at the adjusted stiffness and adjusted damping as shown in equation 4-23. So as you can see, material damping actually reduces the stiffness and increases the damping computed based on the elastic solution. Generally, footings just do not simply rest on soils, but are partly embedded. Embedment results in increase in both stiffness and damping, especially damping. The lack of confining pressure at the surface often leads to a separation at the surface, due to which the entire depth of embedment cannot be considered. So an effective embedment, shown as L in this slide, is considered for the calculations. The soil reactions at the bottom are based on the half-space models like Richard Whitman or Vellet-Sauce models, while side reactions are calculated based on an independent layer of soil overlaying the half-space. These are the equations used for calculating impedance values for the embedment. The dimensionless parameters SU1, SV1, or SU1 and SV2 are taken from the table 4.2, and the values depend on whether the soil is granular or cohesive. The allowable vibration for various types of machines are set by the equipment manufacturer or are specified by the owner or operator. These limits ensure that the equipment functions properly and there is limited damage to it during operation. In case such data is not available, one can refer to various studies and papers published by researchers. One such vibration chart published by Blake is seen in this slide. Based on the operating speed of the machine, the horizontal displacement amplitude computed from the analysis can be plotted in this chart, and one can determine the region in which the performance falls. The description corresponding to each of these regions are given below the chart. So as you can see, if your machine is in the A or B zone, you don't need to worry about maintenance. On the other hand, if it's in the C zone, then maintenance should be done within 10 days and so on and so forth. Here is one more vibration chart from Baxter and Bernard, where based on the displacement amplitude, it grades the operation of the machinery from extremely smooth to very rough. Here is one more chart showing how these different vibration standards compare against each other when it comes to permissible displacements. Let us now see how the machine foundation can be defined in STAAD Foundation Advanced. In this dialog box, you choose the foundation type and machine type as we discussed earlier. The software generates a finite element model of the machine foundation based on the input data. Meshing type and target mesh inputs control that finite element mesh. The software also calculates the natural frequencies of the foundation and compares those to the machine frequency to check for any resonance. In simple terms, resonance is amplification of the vibration effects when operating frequencies of the machine and the natural frequencies of the supporting structure and foundation come close. By default, a 20% separation in frequencies is considered adequate, but you can set your own percentage using the resonance check option as seen here. In this dialog box, you would enter the dimensions of the block foundation along with the pier position and pier dimensions. The machine geometry inputs are only relevant for reciprocating machines. In this dialog box, you get to input some of the machine details like the machine speed and the static weight. You can define the point of application of the machine load, which is usually the CG of the machine. All of the inputs related to dynamic loading are also entered here. As far as applying the dynamic loading is concerned, you can choose from three options, namely direct loading, eccentricity, and empirical method, as already discussed before. Other dynamic analysis related data like material damping and number of modes to consider are also entered through this dialog box. In this dialog box, you need to provide inputs related to generation of the soil springs. As discussed before, you can specify the horizontal and vertical soil spring stiffness as well as the vertical and horizontal damping directly, or you can ask the software to calculate this as per Richard Whitman method or Vellet-Sauce method. You can include the effect of material damping. You can also have the impedance due to embedment considered in the analysis. We have discussed each of these in detail, and so let's now go ahead and run the analysis. Once the analysis completes, you can take a look at the calculation sheet, which provides the details of the vibration analysis. And that brings us to the end of the vibrating machine foundation analysis using STAAD Foundation Advanced. The next foundation we are going to look into is the tank foundation or ring wall foundation. This slide lists the references used by STAAD Foundation Advanced. PIP STE 03020 Chapter 5 outlines the procedure for designing concrete ring wall foundation for tanks, which again is based upon the guidelines provided in API 650 and ACI 318. This slide also indicates the references for the Indian standards. The load combinations can be generated as per PIP STC 01015 or ASC 7. In STAAD Foundation Advanced, you can design self-anchored, or in other words, unanchored tanks, or you can design mechanically anchored tanks. There are a few important differences between the two, especially when it comes to checking for stability. For self-anchored tanks, self-weight of tank and part of the tank content are used to calculate the resisting force to overturning and uplift, whereas for mechanically anchored tanks, you are relying on mechanical anchoring devices like anchor bolts. There is also a difference in the way the twist steel is provided. For self-anchored, the twist steel is provided at the bottom of the ring wall, whereas for mechanically anchored tanks, the twist steel is provided at both the top and the bottom. This slide shows a diagrammatic representation of the loads that are considered for designing the ring wall foundation. First, there is the empty weight of the tank, which includes the weight of the roof, shell, and the floor plate. On top of that, any additional load like dead load or live load acting on the roof or load from miscellaneous attachments are also included. Then there is the product load, which is shown as a pressure load on the floor. If the fluid contained within the tank is pressurized, you would consider that load as internal pressure. There could also be snow load on top of the roof, and finally, the lateral loads like wind and seismic loads. Also, there is going to be lateral pressure on the ring wall from the soil and the product surcharge. Now let's look into the design considerations. The ring wall foundation is subjected to significant amount of hoop tension due to lateral earth pressure. This pressure, which is acting on the right side in this diagram, comes from a surcharge due to product load and from the backfill within the ring wall. On the other side, there is the passive pressure due to soil, but that is usually neglected because its availability is not guaranteed. The slide shows the equation used for calculating the hoop tension and the reinforcement required to resist that tension, along with the associated clause references. In addition to the hoop tension, the ring wall is also subjected to twisting moments due to eccentric loading from the tank shell, product load, soil reaction underneath. This slide shows the calculation for the twisting moment, which is also explained in section 5.6.4.4 of the STE 3020 document. The twist moment is considered to act uniformly around the ring wall as shown here, and tends to push one end of the ring wall outward, thus causing the tension to develop on that face, while the other end is pushed inwards, causing compression to develop in that face. Additional hoop reinforcing is placed in the region subjected to tension. Equivalent longitudinal moment is calculated for the ring wall based on this twisting moment. This is based on this equation 5.6.4.6 of the STE 3020 document. The amount of steel required to resist this moment is then calculated based on the ACI 318 equations. The software ensures that minimum reinforcement requirements as per ACI 318 are met. Total horizontal steel requirement is calculated by adding the steel required to resist hoop tension and the twist. The vertical steel is provided through stirrups. Minimum vertical and horizontal reinforcement requirement is then satisfied as outlined in STE 3020. Here is a snapshot of the relevant section from the code. This slide shows a typical reinforcement detail for the ring wall foundation with the horizontal steel and stirrups that we talked about in the previous slide. A couple of things worth noting related to design of ring walls. Minimum concrete strength should be 3 kSi. Ring wall should be minimum 12 inches wide and minimum 3 feet in height, 12 inches of that being above the grade and 24 inches below the grade. These are of course minimums, and your actual dimensions could be larger. Let us now see how to define the tank foundation in STAAD Foundation Advanced. The input again is wizard driven, which makes the modeling part super easy. A couple of inputs especially important to note in this page are the foundation type, which could be mechanically anchored or self-anchored, as we already discussed. Other than that, you can indicate here as to how you want to input the weight of the product that is contained within the tank. You can directly define the weight, or you can simply define the volume of the fluid and let the software calculate the weight based on that. A few quick facts on the stability checks. As far as overturning is concerned, traditionally ring wall foundations are not designed for the additional overturning moment from the base shear applied at the top of the ring wall. This is because most of the additional overturning moment does not develop due to passive pressure resistance of the soil outside the ring wall, and also due to friction between soil and the vertical sides of the ring wall. Whatever little additional overturning moment may develop is generally neglected. Coming to sliding, unless subjected to extraordinarily high seismic forces and unusual soil conditions, tanks do not slide. If sliding of the foundation needs to be checked, one may account for the resistance to sliding offered by friction between the foundation and the soil, and also the friction developed between the soil contained within the ring wall foundation and the soil underneath. In addition, the passive pressure offered by the soil outside of the ring wall also resists the sliding. However, in case you would like to check sliding and overturning, you can always use the check boxes as shown in this dialog box. In the next page, important parameter to note is the eccentricity of the wall with respect to the ring beam. This dictates the twisting moment calculations as we saw. If you are planning to let the software decide on the width of the ring wall, you can provide a range of values for width along with a width increment. If you already know what the width is, you may set the same value of width for both minimum and maximum. You are also going to provide the height of the ring beam. If you have a concrete slab under the floor plate, you would specify the thickness for that out here. The space within the ring wall could be backfilled with compacted granular fill capable of supporting the tank dead load and the product surcharge load. If that is the case, you would specify the appropriate thickness for the fill. If you do not have concrete slab or the granular fill, simply enter those thickness values as zeros. You can account for weight of any attachment to the tank by specifying that as a percentage of the tank weight. If you are using a mechanically anchored tank, then you would also specify the number of anchor bolts. In the next page, you are going to enter the parameters related to the geometry of the tank. In this page, you are going to enter the loads for the operating condition and also for the test condition. If you would have chosen to directly enter the weight on the first page, then you would directly enter the fluid weight here. Else, if you would have chosen to enter the fluid volume in the first page, then you would enter the volume data here as opposed to the weight. You would also need to specify the liquid height, as the liquid height to the tank diameter ratio has direct impact on some of the design checks as well as freeboard checks. If the fluid is pressurized, you would indicate the internal pressure for both operating and test conditions. In addition, you would also get to define any loads on the roof like snow, miscellaneous dead, and live loads. In this page, you would enter the data related to the wind load generation. We have already discussed about this in other modules, and so I will skip to the next page. In this page, you're going to define the seismic load. You can directly define the impulsive and convective seismic shears and moments, and this can be done for both operating and test conditions, or you can specify the related seismic parameters, and the software would capture the seismic forces and moments based on the guidelines of Chapter 5 of the API 650. In this page, you're going to define the load combinations. Last but not the least, in this page, you can specify the parameters related to the serviceability checks like sliding and overturning, and also the parameters related to the reinforcement design for the concrete ring wall. Once all the parameters are input, we can just simply go and design the ring wall. And once the design is completed, the detailed calculations are going to be available as part of the calculation sheet. So as you can see here, the software lists all the details in the calculation sheet along with the relevant code references. The next foundation type we're going to talk about is the drilled pier. STAAD Foundation Advanced uses the Chapter 4 of the EI 02C097 as the reference. Deep foundations like drilled piers often support substantial amount of lateral loads in addition to supporting axial loads. Whereas design against axial load can be carried out by simple static methods, the design of piers against lateral loads is much more complex as it involves nonlinear soil structure interaction. The way such deep foundations behave depends on the stiffness of the pile, stiffness of the soil, mobilization of the resistance in the surrounding soil, boundary conditions like fixity at the ends, etc. This slide is a representation of a pile with an axial load, lateral load, and a moment. The lateral soil resistance, which is plotted on the right, is simulated through a series of PY curves generated along the length of the pile. As you can see, it is a non-linear function of the lateral displacement y of the pile. X is measured as the distance along the length of the pile here. This slide shows the conceptual PY curve where the soil resistance is plotted along the ordinate and the lateral pile deflection is plotted along the abscissa. The portion between 0 to A is representative of elastic action of the soil, which, as you can see, is only valid for a very small range of displacement. The portion A to B is the nonlinear transition portion, and it is at the point B that the ultimate soil resistance is reached. The determination of the PY curves is a function of the type of soil and also a function of the loading, static or cyclic. Here is a sample of how these are calculated for soft clay submerged in water. It starts with getting an accurate estimate of the undrained shear strength C and submerged unit weight of the soil represented as gamma dashed. Ultimate soil resistance Pu is then computed as the minimum of the values obtained from equations 4-1 and 4-2. J is the empirical dimensionless parameter and is considered as 0.5 for soft clay. Deflection Y50 at half of the ultimate soil resistance is computed as per the equation 4-3. Epsilon 50 is the strain computed at half of the maximum principal stress and is taken from table 4-1. Eventually, the PY curve is generated based on the equation 4-4. All of these equations are for static loading case and is shown in figure A. Similarly, the figure B shows the PY curve for cyclic loading. A series of fourth-order differential equations of the form as shown in the first equation in this slide are solved iteratively at multiple locations along the length of the pile. The nonlinear properties of concrete and soil are accounted for in the analysis. The solution is iterative as both the soil stiffness and the stiffness of concrete changes with the pile displacement. Once a converged solution is obtained, the displacements, moments, etc. at all points along the pile are known. The actual moments are then compared against the bending capacity to check if the pile section is adequate or not. The tip resistance and skin resistance of the pile are also calculated and summed up to obtain the unfactored and factored axial capacity of the piles. Now let's take a quick look at the way one can set up the lateral analysis for drilled pier. In this dialog box, apart from specifying all the project-related information, one can select the pile type as drilled shaft or a driven pile. Select the units and design code, and then choose the loading type, which could be static or cyclic. Cyclic would be typically used when these piers are subjected to lateral loads from vibrating machinery. In the next dialog box, one needs to specify the geometry of the pier, which is used by the software for calculating the stiffness of the pier. It supports a variety of section types. For example, for drill piers, the section could be circular cross-section with or without casing, or with casing and a core. It could be a rectangular cross-section without a casing. Or one can even define a user-defined cross-section, in which case one can enter the cross-sectional area, moment of inertia, etc. directly. Depending on the type of the section chosen, one needs to define the other parameters. For example, if there is a casing, then the material for the casing needs to be defined. The reinforcement information needs to be entered as well. The section length defines the length of the pier, which has been assigned the current cross-section. In case there is a variation of section type with depth, one can add additional sections as well with associated section lengths for each. In the next dialog box, one can enter the soil properties. One can choose from a variety of soil types for sand and clay. The relevant soil parameters will be listed by the software. For example, if one chooses the clay, the software would list the parameters like cohesion and epsilon value. On the other hand, if one chooses sand, it would be the angle of friction. Either way, the parameters will be populated with default values. One can change the values as needed based on the geotechnical information obtained from the site. If the site has multiple layers, each consisting of different soil types, one can define that by choosing the Add Layer option. One can provide appropriate depth for each layer and assign separate soil parameters for each layer. These parameters are subsequently used by the software for generation of the PY curves for each layer. In case one needs to factor the values generated for the PY curves, one can use the PY multiplier options. Next is the load input dialog box. The purpose of the axial load specified here is to consider its effect on the bending stiffness. One can enter the shear and the moment on the pier. Shears can be specified by either directly entering the shear force or by entering the lateral deflection. Similarly, moments can be specified directly or through rotations. The final dialog box lets one define the design parameters like strength and modulus of elasticity of reinforcement and concrete. For batter pile, one can indicate the angle between the vertical and the pile axis. In case the ground is sloped, the angle between the ground surface and the horizontal can be specified too. The number of increments dictate how many locations along the length of the pile the PY curves are generated at. A number of inputs related to axial load are also entered here, like the critical depth ratio. The critical depth is the soil depth at which vertical stress appears to become constant, and critical depth ratio is the ratio of the critical depth to the pile diameter, which typically ranges from 10 to 20. One can either define the ratio directly or have the software calculate the same. One can specify what percentages of tip resistance and skin resistance may be considered in calculating the axial capacity of the pile. The factors of safety for the axial loads related to end bearing and skin friction can also be input. Finally, one can neglect the skin friction developed by certain depth of soil at the top and at the bottom of the pile. For example, the first 5 feet of soil plus any backfill is generally neglected when it comes to computing the skin friction. Similarly, the bottom 5 feet is also neglected by the software from the skin friction calculation, and one can override these if needed. Once all these inputs are provided, one can click on the finish and then proceed with the design. Once the design is completed, the calculation sheet lists all the details of the calculations. As you can see, there are a series of PY curves that has been generated at different depths along the pile, and followed by that, there are the lateral analysis results, followed by the capacity checks. That brings us to the end of this webinar. If you have any questions regarding this webinar, please reach out to us through the Q&A page of this webinar posted on the Bentley Communities Forum as shown in this slide. I would like to end today's webinar with a slide showing the top 10 capabilities of STAAD Pro Connect Edition, which I am sure would be of great value to you. The STAAD Pro Connect Edition is seamlessly integrated with STAAD Foundation Advanced. If you haven't had the chance to update to the STAAD Pro Connect Edition, please do so at your earliest convenience and enjoy the benefits. Thanks for watching.